I have already mentioned the assessment report 6 from the IPCC that has been released, and some of them are still in the final draft version, or draft version and not final version, however it is worded. We also have included some of this podcast elsewhere, especially the physical science basis. The other two working groups got released a little bit later. So in this course on the Introduction to Climate Change and Climate Science, or Climate Science and Climate Change, I wanted to include summaries of all three working groups again, to keep them in one place. So they start the working group 1. So as you know, IPCC, the Intergovernmental Panel on Climate Change, splits itself into 3 working groups. Working group 1 works on the physical science basis. Working group 2 works on mitigation. Working group 3 works on adaptation, vulnerability, risks, and so on. And they provide fairly comprehensive synthesis of all the related science that has happened since the last report was released in 2014 to the deadline they had before this report had to be finalized and sent to the press. Okay, so some of these you already know, but let's go through them again anyways. Changes in global sea surface temperature relative to 1850 to 1900 used as a base period. Changing the base period changes the numbers just a little, but doesn't change the story, especially the impacts that are being observed. Okay. So change in global sea surface temperature as decadal averages as reconstructed here and observed 1850 to 2020. So from Common Era year 1 to 2000, and then there is Industrial Revolution onward, and you can see that the reconstructed time series has increasing, it has a large uncertainty or variance between various estimates, and maybe somewhat increases as you go back in time. So various proxies are combined for ice core, tree rings, various lake sediment information, and so on, whatever is available. Okay, so here is the range: warmest multi-century period in more than 100,000 years. So from the beginning of the Industrial Revolution, or with respect to this base period, we have warmed about 1.2 degrees centigrade. So the warming is unprecedented in more than 2,000 years here. So you can keep that in mind as a context. And of course the biggest need, requirement, or obligation is to show that this is in fact related to human activities. So changes in global sea surface temperature as an annual average as observed and simulated using human and natural, and only natural factors, both 1850 to 2020. So this is what we referred to before as detection and attribution, if you remember. So you take the observed time series as before, now focused on the 1850 to 2020 period, and you make sure that the number of models that have been used are able to reproduce the observed trends, and the internal variability, or the year-to-year and decade-to-decade variability that is due to natural variability or a combination of natural and human activities is not reproduced by the models, in the sense that in the observed record 1997-98 or 2014-15 are big El Niños. In the model simulations, there will be El Niños and La Niñas. There are strong El Niños, weak El Niños, and so on. But a particular year in the model simulation during its 20th century simulation will not correspond to exactly to the observed year, because you are mostly capturing the forced variability and the internal variability or the natural variability in the climate models in these simulations are not forecasts, so you cannot match exact year to year. So you can see that the observed trend is captured with a range here of various models, and the simulation here is done with natural forcing such as volcanoes, solar variability, land use change, and so on, some of which is human, and human forcing, which is mostly greenhouse gases and some land use change, urbanization, conversion to agricultural land, deforestation, and so on. So the idea is that when we have human and natural forcings, we can get the observed simulation reasonably well, which gives us confidence to say if we take out the human contribution in terms of radiative forcing or additional energy that's being trapped, what happens. And you can see that the warming from about the 1950s essentially disappears. So simulated natural only, so solar and volcanic, does not produce this warming we have observed, which is a clear indication that the detected warming over this last many decades can be unequivocally attributed to human contributions to radiative forcing. So here again, observe the warming 2010 to 2019 relative to 1850 to 1900. So just the last decade. Obviously there has been a acceleration of the warming of sorts, and it's a good decade to use as a baseline of sorts. So here it is of about over 1 degree centigrade with some range of error or standard deviation, you can think of that way. Contributions to warming based on two complementary approaches. So aggregated contributions to 2010 to 2019 warming relative to 1850 to 1900, assessed from attribution studies like this, where models remove various forcings and see how much warming can be attributed to the total human influence, well-mixed greenhouse gases like CO2, other human drivers like land use change, cement production, etc., solar and volcanic drivers, which are around the zero line, plus and minus, and internal variability, which is things like El Nino and La Nina, Atlantic multi-decadal variability, Pacific decadal variability, and so on. There is now a debate about whether Atlantic multi-decadal variability is a real climate mode or a statistical artifact, and so on. But leaving that aside, the main message here is that the contribution, the total contribution, and the well-mixed greenhouse gas contributions plus other human drivers are well above the natural drivers and internal variability. And you can see here that the greenhouse gases caused a warming, whereas other things like land use change, albedo changes, etc., caused a cooling, so the net warming is less than just the greenhouse gases. You can also look at it as contributions to 2010 to 2019 warming relative to 1850 to 1900, assessed from radiative forcing studies. So you estimate the additional radiative imbalance caused at the top of the atmosphere because of the various increases in greenhouse gases like CO2 here, methane, nitrous oxide, halogenated gases, nitrogen oxides other than nitrous oxide, so NOx goes in there, volatile organic compounds and carbon monoxide, sulfur dioxide, which is scattering and cooling, so are the NOxes, organic carbon here, ammonia pretty much close to zero, black carbon has a large range as well, land use, reflectance, and irrigation, so albedo changes and other contributions from land use, deforestation, agriculture, and irrigation, and aviation contrails, which are very high in terms of the contribution per flight, or there is various ways in which to look at their impact, and their impact will continue to grow, but right now they are a small fraction as well. So these two different ways of doing basically give you the same message, that the warming due to greenhouse gas increases by human activities is a significant contributor. So the types of observed changes in this report are done slightly differently than was done in the previous reports. So you can see that the globe has been split into these regions: North America, Central America, small islands, South America, Europe, including Greenland here, Asia, Australia, small islands, and Africa. And each continent is then divided into these hexagons as Northwest, Northeast, Greenland, Iceland, Eastern North America, Central, Western, and so on and so forth. And the color codes here are for types of observed change in hot extremes. So this magenta color corresponds to increases in hot extremes, and 41 of the regions here show an increase, and none of the regions across the world show any decrease. On the other hand, there are regions, two of them, where agreement is low in the type of change, whether it has been an increase or a decrease, and there are regions like here and here where the data is limited, or there have been no attribution studies to say anything confidently. The confidence level is indicated here as well. 3 black dots indicate high confidence in the attribution, 2 dots medium, 1 dot low due to limited agreement between different studies, and the open circle is due to low but due to limited evidence available. So you can see that there is a low due to limited evidence in both these places where there is limited data and or literature. And let's zoom into our region here, South Asia, and you can see that there is high confidence in attributing the increase in observed hot extremes to human contribution. If we then move to synthesis of the assessment of observed change in heavy precipitation, we've already talked about how difficult it is for models to do precipitation and how often it is difficult to get precipitation data to the same extent as temperature data, especially because precipitation tends to be very local and models do temperature very well, whereas they have a harder time doing precipitation as well. So looking at type of observed change in heavy precipitation, now you can see that there are only 19 regions where there is a increase in heavy precipitation, but none of the regions show any decrease. But the number of regions with low agreement or limited data and or literature are large here compared to the heat extremes, and the confidence in human contribution also varies quite a bit. There are basically no triple dots in anywhere here. There are a few 2 dots, so medium confidence. Lots of regions have low confidence due to limited agreement or low confidence due to limited evidence. So precipitation is a problem for sure. And on the other hand, you can see that South Asia here had very high confidence in the increase and attribution of heat extremes to human impacts, whereas in precipitation the confidence is low, even though observed changes do indicate an increase in heavy precipitation. That's true for most of these regions. Actually, I'm wrong. Here is one region, Northeastern Europe, which shows high confidence in attribution, basically because of many studies and data available as well. Okay, so keep these in mind just in terms of the differences. The other thing that is looked at is so-called agricultural and ecological droughts, which are beyond the meteorological droughts. Meteorological drought is when you have deficit rainfall with respect to long-term climatology, but if the evaporation and lack of precipitation begins to result in loss of soil moisture down to something like root depth, then there is something called the column total column soil moisture that is defined to indicate agricultural and ecological droughts. Again, the story is quite mixed in terms of increases. There are about 12 regions. There is one region that shows a decrease in northern Australia, and most of the other regions have low agreement in the type of change and low agreements due to limited data and or literature, and again confidence levels are typically low. In the Mediterranean there is medium confidence, Western North America there is medium confidence. This has become a poster child for long lasting severe drought, with contributions from man-made climate change as well as man-made water management issues as well. But you can see the rest of the places basically have single dots indicating low confidence due to limited agreement, or some open circles like here in the Pacific Small Islands where there is low agreement or low confidence due to limited evidence. Okay, so these are the various names of the regions that I did not bother to make explicit, but you get the sense. Okay, so maybe I can leave this here and come to what can be expected in the future in the next podcast, because that goes into what we have already discussed in terms of creating scenarios. As we remember, in the IPCC AR5 released in 2014, so-called representative concentration pathways were used, and then the shared socio-economic pathways evolved, and in AR6 there is a combination of shared socio-economic pathways and RCPs used, and we will talk a bit more about that in the next podcast. Okay, so let's come back to that in the next podcast.